Webinar. This is part of the AI and data theme of the ACE Network talk series. I have the great pleasure to introduce our speaker for the day, Giordano Scarciotti. Giordano is an academic within the Control and Power Group at Imperial College in London. Let me also say a few words about his career path. So he obtained his first degree at the University of Rome. Since then, he has been with Imperial, obtaining also an MSc in Applied Math, as well as a PhD from Imperial College. So he has received several awards within the years. Among these, I will mention two. His PhD thesis award from the IET, that received the IET Control and Automation Dissertation Prize, as well as an Imperial's Award for Excellence in Teaching, and multiple others. Today, his presentation has the intriguing title, One Equation to Rule Them All. So Giordano, we look forward to it.
Thank you. You can hear me, right? Yeah, okay. Thank you very much for the introduction, Kostas. I'm very happy to give this talk in this series. Yes, the title is interesting. Of course, it's a reference to the Lord of the Rings. I have to say this because I understand that it may be a generational thing to know or not. I gave this seminar already various times in China. So this is the first time I give this seminar in this part of the world. And people pointed out that actually it's a very bold title, which is true. But I think it's also quite descriptive of the method, really. So let me first of all mention that this is a joint work with Junyo Mao and Emir Williams, which are two of my PhD students, and with Tulasi Malvaganam in the Department of Aeronautics as a professor in control engineering. So I will start first with the model-based theory, and then I will move to the data-driven version of this theory. Okay, and the equation that is going to rule them all is the Sylvester equation, which is this equation that you see here on top, where we have some given matrices A, B, and C, which are not the A, B, and C of the system. Okay, so they are just random, generic matrices A, B, and C. And then we have the unknown, so the matrix that we do not know, which is pi, okay, which we want to compute. And it's well known that if the spectrum of A and B is disjoint, which means that A and B do not have any common eigenvalue, then this equation has a unique solution. A special case of the Sylvester equation is the Lyapunov equation, which is much more well known. But in the case of the Sylvester equation, pi in general is a rectangular matrix, so it's not a square matrix. Now, the Sylvester equation plays a role in a lot of different problems, really. For instance, it appeared in the original paper of Leuenberger on observer design. So this is based on the idea of finding a change of coordinate. And this change of coordinate, the matrix of change of coordinate solves a Sylvester equation. It appears in autoregulation. So maybe some of you saw this in the regulatory equations, which is made of two equations. One is the Sylvester equation and one is the error zeroing equation. It appears in pole assignment, the Star-Batz decoupling, in cascade stabilization, specifically in the forwarding method, and in model order reduction, specifically in moment matching. So you can see that this equation appears in a lot of different control theoretic problems, from control to analysis to modeling. And actually, together with Daniele Astolfi at CNRS and John Simpson-Porco, we sort of put together all these applications, and we wrote a paper which has been accepted a few months ago on transactional automatic control, in which we list all the possible designs that you can do with the Sylvester equations and its dual form that I will mention in a moment. And so if you are interested in having a general overview of this, you could look at those at that paper. Now, there is also a nonlinear version of this equation. So all these problems have a nonlinear version, most of them, not the pole assignment one, but most of them have a nonlinear version. And in that case, the Sylvester equation becomes a partial differential equation that expresses, as we will see, an invariance property of a certain manifold. And for this reason, the nonlinear version of the Sylvester equation is often referred to as invariance equation. And it plays a role in all those problems that I mentioned already. Now, to understand why this equation is so fundamental, let me explain how this equation arises, a possible interpretation, and in particular, a dynamic interpretation of this equation. So let's consider the case in which we have a linear system, and we drive this linear system by means of an exogenous system, which we call signal generator. So it generates signals which are going to drive my linear system. And if I interconnect this generator with the linear system through the input u equal to L times omega, where omega is the state of the generator, then it's possible to show that there exists an invariant manifold, in this case a subspace, an invariant subspace, described by, all the points x omega that satisfies the equation x equal to pi omega, where pi solves a Sylvester equation, okay? So we have this invariance property, first of all, and in addition, if we have more properties on the system and on the generator, then we will also be able to describe the steady state of this interconnection. And in particular, the steady state will be of the state x is going to be equal to pi times omega. So let me tell you a bit about the assumptions here and why this is the case. So to have just the invariance property, the only assumption that you need is that the eigenvalues of A and the eigenvalues of S are not common, because in that case, then this Sylvester equation is well defined and this invariance property is satisfied. Just to clarify, I don't know what is your background, but invariance means that if the solution of your system X starts on the subspace, then it will stay on the subspace, which means that if x of 0, for instance, is equal to pi times omega 0, then you're always going to satisfy the equation x of t equal to pi omega of t for all times. Now, by making a change of coordinates, it's possible to show that x of t will always have this form equal to pi times omega, plus e power at times the distance from the manifold, if you want, from the subspace. And if, in addition to having no common eigenvalues, we have the assumption that A is Hurwitz, so all the eigenvalues of A are on the left-hand side of the plane. In general, we want that the system is asymptotically stable, essentially. And if the generator generates trajectories which are persistent in time, like, for instance, sinusoids and steps, then what we can clearly see is that the pi times omega will describe the steady state, because e power at will go to 0, because A is Hurwitz, and then this transient will disappear, and what we are left with is pi times omega. Pi are signals which are persistent in time, like sinusoids and steps, and that means that this is going to be the steady state of our interconnection. And this shows clearly why then this Sylvester equation is important, because it describes the steady state of a system, and that means that all problems like observer design, in which we want to reconstruct the state of the system asymptotically, or regulation, where we want to track a reference asymptotically, they're all based on the idea that we can actually describe and characterize the steady state of the system. Now, as I mentioned, there is also a nonlinear version of these results, in which is completely analogous. Given a system, this time a nonlinear system, if we drive this system with a generator, then there exists an invariant manifold, which is described by x equal to pi of omega. So now it's a nonlinear mapping, where pi is the solution of a partial differential equation, which is the clear nonlinear version of the Sylvester equation before. And as before, if we have additional dynamic properties on the equilibrium point of the system and on the trajectories of the signal generator, then we can show that the steady state of our interconnection is characterized by pi, which is the solution of this of the PD. Okay. Now, before moving on, I want to mention that actually in the literature, there are two Sylvester equations that appear. One, which is the top one, which is what we call dual Sylvester equation. And then we have the standard, the one that I already introduced before, the A pi minus pi b equal to c, which is what we can call the primal Sylvester equation. Now, you can clearly see that algebraically they are the same equation. One is the transpose of the other. But the point is that these equations arise from interconnection of systems. And if the systems, if the matrix A has the same meaning in both equations, then the two equations are not anymore equivalent, but they describe a different interconnection, as I will show you in a little bit. But the point is that depending on the application, one equation or the other equation appear. For instance, the top equation appears in observer design, it appears in cascade stabilization problems, while the second equation appears in output regulation, it appears in the direct moment matching method for model reduction, and so on. Okay? And also for this top equation, there is a nonlinear version, which again is a partial differential equation, and nonlinear versions of the various problems exist. Just to clarify, so essentially we can interpret these Sylvester equations depending on various system interconnections. We have seen already the top interconnection, which for which we know that the solution of the Sylvester equation pi is going to describe the steady state behavior of, in this case, the output of this interconnection if we multiply by c. If instead we use the other interconnection in which the system drives a filter, for instance, then the dynamic property that we're going to look at is the steady state of Z, so the steady state of the filter, of the state of the filter. And in that case, we will get that M, which is the solution of the dual Sylvester equation, will appear in this steady state. So both pi and M describe the steady state of interconnections, but the interconnections are different and they're used in different problems, depending on what is really useful. There is also a dual interconnection, which I'm not going to explain, but this appears, for instance, in the problem of two sudden moment matching, in which both M and pi will play a role, as you see here. Now, the key message of this talk, since I already spoke for almost 15 minutes, and I'm scared that I already lost you, is that, okay, the Sylvester equations play a key role in a variety of analysis and design and modeling problems, as I mentioned. And so the idea of the talk is the following, is that if we design a data-driven method that is specifically geared towards finding solutions for Sylvester equations, then we could solve all these problems from the same point of view. So the central idea essentially is to consider all these different problems and decompose them as interconnection of systems, two or multiple dynamical systems, or if you want, decompose your problem in multiple steps, in which one of the steps corresponds to solving the Sylvester equation. And then using that step, we can solve, using the data-driven version of the Sylvester equation, or actually the data-driven version of the solution of the Sylvester equation, then we can solve all these problems, tracking, regulation, observation, model reduction, stabilization, and so on, from data, but just plugging in some other missing elements or some variations. And one interesting aspect is that because the framework that I'm presenting is a decomposition framework, we can easily propagate the error through the decomposition. And so we can, for instance, quantify the error at the end of the design. So for instance, the end of the stabilizing controller for the cascade as a function of the noise or process noise or error, which we have at the beginning of the process. So this is the key message in case I lose you and you won't follow the rest. That's essentially what I'm going to present. So let's start with some preliminaries. Here I introduce the Sylvester equation, yet using a different notation. So this notation is is essentially referring specifically to the two systems which I'm going to interconnect. So sigma 1 is the system A1, B1, C1. Sigma 2 is the system A2, B2, and C2. And then I'm going to interconnect these two systems as sigma 1 driving sigma 2. So if sigma 1 drives sigma 2, the Sylvester equation resulting from this interconnection is given here at the top. It's A2 theta, where theta is the unknown, is the solution of the Sylvester equation, minus theta A1, so A1 is the dynamic matrix of the first system, equal to minus B2 C1, where B2 is the input matrix of the second system, and C1 is the output matrix of the first system, okay? Now, when I interconnect these two systems, as I said, we're going to induce an invariant subspace, which is given by all the points x1, x2 that satisfy the equation x2 equal to theta x1, where theta is the solution of the Sylvester equation. And then here the idea is that without assuming additional properties on A and A1 and A1 and A2, I'm going to define a new coordinate, which is the distance from the subspace. Okay, so it's x2 minus theta x1. And I call this distance zeta. And then I compute the dynamic of zeta. So I compute zeta of k plus 1. We are in discrete time here because we're going to do a data-driven approach. And so I assume that we are in discrete time. And okay, it's just algebra here. You do the computation, you replace what you know, and so on. At a certain point here, when you have B2, C1 minus theta A1, we're going to use the Sylvester equation to replace this with minus A2 theta. We do the computation, and we end up with this last line, which is A2 equal to minus theta B1. And this equation appears in all the problems that I mentioned before. But here is the key difference, is because before I mentioned that there is a primal and a dual Sylvester equation. Now we are dealing with these two equations together, actually. So we're not going to make a distinction between primal and dual, because we can change from one case to the other depending on whether there is an input or not over here. So specifically, in the case in which U1 is identically equal to 0, then what we have is just that the error dynamic is zeta equal to zeta of k plus 1 is equal to A2 zeta of k, which if our system, second system, is asymptotically stable, then means that this error goes to 0 and we're going to end up on the manifold. This is the case, for instance, in applications like model reduction by moment matching, the direct interconnection. We actually have exactly this property that shows up. In other problems, like for instance the Cascade stabilization, U1 is not equal to 0, is not identically equal to 0, and is used to make the A2 system asymptotically, stable asymptotically, which again will drive the error from the subspace to 0. So in one way or the other, because of the setting of the problem, we will always end up on the subspace for one reason or the other. Okay. So this was the introduction, the preliminaries, and now we move to the data-driven version of these results. So we're going to assume that we have collected data of our system. So we collect data from x of 0 to x of capital T, and we construct two data matrices. This is standard notation in the data-driven control, which is that capital X minus indicates the collection of data from the initial time 0 to capital T minus 1, and x plus is the shifted version, is from x1 to x of capital T. And this notation holds true for any signal. So for instance, if I have u of t, then capital U minus indicates the data version of this matrix from 0 to capital T minus 1, and so on. And so this is the first result, okay, which is how we can compute the solution of the Sylvester equation from data. The framework is essentially the framework which has been initiated by the Persis thesis. So it's that kind of framework in which we transform our control problem into an optimization problem. And let's try to explain this result. So here what we have is that we have our system sigma 1 and sigma 2, and the assumption is that we do not know sigma 2, we just have data, while
sorry, Giordano.
I think Giordano, you have accidentally muted yourself.
Yeah. Okay, can you hear me?
Yep.
Yeah. Oh, what is the last thing that you heard?
I think you were muted only for a few seconds.
For a few seconds, okay. So let me explain this result, okay? So here we have that sigma 1 is driving sigma 2, as I said before, okay? And sigma 2 is unknown, so is we just have data. Sigma 1 is available from previous steps. So by available from previous steps, I mean that you need to think that this computation of the solution of the Sylvester equation is a middle step in a procedure. And that means that sigma 1 will always come from the previous step, from one reason or the other. For instance, in the case of model reduction by moment matching, sigma 1 is the list of interpolation points, gives the list of interpolation points which is decided by the user, and that's why it's available. If instead we look at the cascade stabilization problem, sigma 1 comes from is the closed loop version of the first system, which is obtained from data, but at that stage will be available. So for one reason or the other, sigma 1 is always available from some previous knowledge, as we will see later. So it's not a restriction actually to say that sigma 1 is available. It's possible to also do the version of this result in which sigma 1 is not available. It is in the paper, in the appendix, but it's basically useless because in any result, in any method that we developed, sigma 1 for one reason or the other is always available. We make the assumption that x2 minus and u2 minus is full rank, so that the data is sufficiently rich. So this assumption can be made weaker. So if you are familiar with this framework, you can relax this rank assumption with an informativity assumption. So we can discuss this later. So it is not so this rank condition is just sufficient and it's just simple to use, but it can be made weaker. And of course, we also assume that the eigenvalues of A1 and A2 are disjoint, so that they do not have common eigenvalues, because otherwise the Sylvester equation does not have a unique solution. Then the result is essentially that there exists that any matrix G theta that satisfies these two equations, 3a and 3b, is such that theta, the solution of the Sylvester equation, is x2 minus times G theta. And conversely, the solution of the Sylvester equation can always be written in this form. Now, let me explain these equations, where they come from. And the idea is the following. We take the Sylvester equation and we factorize theta C1. So just to remind you, the Sylvester equation in 5 was written as A2 times theta plus B2 C1 equal to theta A1. That's the Sylvester equation. And what we do here is that we factorize this in A2 B2 that multiplies the matrix theta C1 equal to theta A1. And now we remember that we assumed the rank condition on x2, u2. The rank condition here is that x2 minus and u2 minus of the data is essentially is full rank. So it spans the entire space, which means that, of course, if it spans the entire space, a linear combination of the columns can give anything. And specifically, what I want is that it gives theta C1. So G theta is nothing else that is the weights of the linear combination of the columns of a basis for the space that gives any vector. In particular, I want that it gives the vector theta C1. Okay. So as long as x2 minus u2 minus is full rank, you can always there is always a G theta that has this property. Now, what I do is that I replace this into the previous equation, and so I have A2 B2 equal to x2 minus u2 minus times G theta. And now what I do is that I do the computation. A2 times x2 minus plus B2 u2 minus is equal to x2 plus, which I replace here. So x2 plus times G theta is equal by 5 by the Sylvester equation to theta A1, which is then equal to x2 minus G theta A1 because I'm using the first row in 6. So I obtain the equation that x2 plus G theta is equal to x2 minus G theta A1, which is the first equation 3a. And for the second equation, so the equation 3b, is nothing else that C1 U2 minus G theta that I read from 6. So that's how I get the two equations. So that I know that if I can find G theta, I find the solution of the Sylvester equation, where the 4, so theta equal to x2 minus G theta, is again read from the first line of 6. So it's very simple procedure. And the point is that this is just 3A and 3B is just a bunch of matrix equalities, which you can solve with a convex optimization toolbox. So for instance, CVX pi or CVX if you use MATLAB, and you can easily solve this and find the solution. Now, as I mentioned, the rank condition can be relaxed, and the idea here is given in 6. We don't need that x2 minus and u2 minus is full rank. What we need is just that x2 minus and u2, what we need is just that theta c1 is in the image or in the column space of x2 minus u2 minus, because if that's the case, then we can find the weights such that we can get theta c1. Okay, so this should be clear. Okay, so we can relax the rank condition. We can get an informativity condition. So x2 minus u2 minus has to be informative for solving the Sylvester equation. And just to clarify, these two conditions are not equivalent in this specific problem. Okay, so the informativity condition in many problems is actually equivalent to the rank condition, like for instance in observer design, but they're not equivalent in state feedback design or for instance in this case. So it can be made sharper. What about noise? So let's do an error analysis. So all the results presented so far is in the case in which there is no noise. Let's consider the case in which there is noise. So we consider the case in which the sigma 2 system has some process noise, so d2 of k. You can think of this as a nonlinearity, for instance. We assume that there is noise on the measurements of the states. So we have x2 bar, which is x2 of k plus some noise. There is noise on the input. And we can also assume, so I said that we know sigma 1, so A1 from a previous step, but the previous step usually it's again the result of a data-driven process, and so that A1 can actually be affected by uncertainty, and so we consider the case in which there is A1 bar, which is the real A1 plus some uncertainty. So we compute the dynamic of the measured x, so x2 bar, and this can be written as in the following way, so as a copy of the real dynamic minus or plus some error noise, which is this R2, which is essentially the sum of all the various noise terms that we have here. And then capital R2 minus is the data-driven version, the data collected version of R2. So how do we do the error analysis? So essentially here the idea is that we now compute again the solution of the LMI, not LMI, because this is a linear matrix equality problem that we obtained before. But now we know that the various matrices that are involved are actually noisy matrices. And we will end up with a noisy version of theta, which is theta hat. And then we define the error between theta and theta hat, so delta theta. And the result that we can prove is that actually this delta theta satisfies as well a Sylvester equation. So the noise, not the noise, the error delta theta satisfies this Sylvester equation given in 8. And this is important for two reasons. The first reason is that this shows that the error delta theta is unique. This is not the case for the error on the G, because if you compute the error on the G, so the difference between G theta and hat G theta, that error is not unique because G theta is not unique. But the delta theta error is unique because it satisfies a Sylvester equation, and the Sylvester equation has a unique solution if A1 and A2 have no common eigenvalues, as we assume at the very beginning to have a well-defined solution. So the error is unique, and then we can use the Sylvester equation to bound the error, so to compute a bound by simply using norms properties. And we end up with that the norm of the error is less or equal than this expression here. Now, let me explain this expression. So we have the Frobenius norm of the computed G theta hat that multiplies some stuff that we do not know actually, because it's the error, it's the noise plus the delta A1 that we do not know, and divided the smallest singular value of this matrix over here that again requires that we know A2 and A1 which in general we do not know. We may know A1, but we do not know A2. So there is a bunch of stuff that we do not know, but what is important is that this error bound has this element here, g theta hat, the Frobenius norm of g theta hat, which means that actually we can reduce and we can minimize this bound, even if we don't know the bound. And the idea is that instead of solving simply the feasibility problem of finding any g theta hat that satisfies 7, we can solve a minimum norm problem, so the minimization of g theta hat in norm, subject to the constraint that 7a and 7b is satisfied, okay? And this will minimize the error bound. Okay, so this essentially is the core of solving the Sylvester equation, and now we're going to apply this in the cascade stabilization problem. Okay, so the first of several problems that we solved using this framework, and today I will probably talk just about the cascade stabilization. I want to point out that this is actually a very long work because of the nature of the work, in which for one equation you can solve so many different problems. Every problem takes some time to cover. And so in the end, we wrote this in 2 papers, so part 1 and part 2, that covers just these 3 problems. But there are many other problems that can be solved with this approach. We are also working on those problems. But if we waited for solving all the problems, then we would never finish the paper. That's why we cut it at 3 problems. And for the talk today, I will cut it probably at just the first problem, the cascade stabilization. And I will give just some ideas for what concern the other 2 problems. So what is the cascade stabilization problem? So the cascade stabilization problem is the problem of having 2 systems that are connected in cascade, so in series, and we want to stabilize the cascade by being able to control only the first system. So we have the x1 system in which you can control u1, but for the second system, x2, you do not have an input. The input of x2 is b2 x1, is the state of the first system. Okay, so this is the setup. Where does this problem appear? So this problem appears for various reasons. One is the case in which you have a bunch of actuators and a bunch of sensors, so physically different systems, and so you want to treat them in a separate way, or because of a specific procedure. For instance, this kind of structure appears in output regulation. When you design the internal model, then the first system may be your system that you want to regulate, and the second system may be the internal model. Okay, so that's for instance a possible application. Because of course, one thing that you may think is that why do I bother to solve the cascade problem when I can just consider this as just a huge linear system? So those are some reasons, but actually there is also data-driven reason, because as I will show you, if you solve the cascade problem rather than the monolithic problem, in which you consider this as a unique system rather than the interconnection of 2 systems, you will require more samples. Okay, so there is a difference in the amount of samples that you require, and that's because the spoiler is that we require less samples because, of course, we exploit some structure in the cascade. Now, what is the idea behind cascade stabilization? So we are going to look at the method called forwarding. And the method is that we take u, and u is the sum of 2 terms, n1 x1 and n2 some stuff. N1 x1 is just a feedback of the first system, and we construct n1 to stabilize a1. Okay? Then what we do is that we use the Sylvester equation to compute a change of coordinate. So we find the invariant subspace associated to the interconnection. And we know, as I explained before at the beginning, that invariant subspace is encoded by the solution of the Sylvester equation, which here I call upsilon c, which solves the Sylvester equation 11, where sigma 1, as I mentioned before, sigma 1 is a1 plus b1 and 1, and sigma 2 is a2. And then once I define the manifold, the subspace, what I do is that I design the second controller to drive the dynamic of the error to 0. So to go to the manifold, that's the idea, right? If I write the system in the new coordinates, I have x1 and zeta, which have a triangular structure. So what is happening here? So the idea is the following. I design U, first of all, to stabilize the first system. Then I know that the interconnection defines an invariant subspace, which is given by x2 minus epsilon x1. And then I construct a controller that drives the error from the subspace to 0. So that means that x2 will converge to epsilon c x1. But x1 goes to 0, and so also x2 goes to 0. And so everything goes to 0, and I stabilize my cascade. And this is evident from the triangular structure over here. I can design N1 to stabilize the first system. I can design N2 to stabilize the error dynamic. So this A2 minus epsilon C B1 is what I showed you before over somewhere. Over here is this thing here, which is always true, okay, as long as the Sylvester equation is defined, okay? And so then you design N2 to stabilize this error. And so, okay, this is a triangular system. And so that means that the whole thing is stabilized. So that's the basic idea of the forwarding method. And now we want to do this from data. How do we do that? So first of all, we want to stabilize the first system. And that's can be done from the literature. From the literature, we know that we can solve from data. We can stabilize a linear system. The idea is that we take A1 and B1, so the matrices of the first system, and we write this with a data representation, which is given here. We don't want to use this because this is essentially system identification. So we don't want to use these formulas, but these formulas are used in the literature, in the paper of the Persis thesis, to actually show that you can write a closed loop representation of A1, B1, and 1, where this closed loop depends on this G and 1, so this parametrization G and 1, where you can find this G and 1 by solving a linear matrix inequality over here, okay? So, okay, if you're not familiar with this, I don't want to explain the whole thing here, but the idea is that you can stabilize a system, a linear system from data, by solving an optimization problem that is completely based on the data and without going through the identification step. Now, what we want to do, what we took care of in our work when we talk about the data-driven solution of the Sylvester equation and all these methods, is that we never use the pseudo-inverse as well. So we do not use at any time the system identification step, but we always find the solution directly from data, okay? Now, the key message here is that, okay, we know how to stabilize the first system from data from the literature. The second step now is to solve the Sylvester equation from data. And this is an application of the lemma that I showed at the beginning of this talk. And this 18a and 18b is nothing else than those two equations that I shown before. So let me go back before over here, is these two equations here, where A1 and C1 now are replaced with x1 plus gn1 and the identity. The identity, because you see that here the interconnection between the first system and the second system is just the state, and so it's just the identity. C1 is the identity. And x1 plus gn1 is obtained from data from the first system. So you can clearly see that, as I said, assuming that sigma 1 is available is not with loss of generality. Because of the structure of the problem, this information still comes from data from a previous step. So now what we're left with is just the need of solving this, which as I said, can be solved using CVX, VXPy, or any other toolbox that you want to solve. This will give us the solution of the Sylvester equation. And now what is left is to do the change of coordinate. So we take the data matrices, we change the coordinates using the solution of the Sylvester equation that we found from data. And we found the data of the error. So this can be found directly from the available data. We find the data of the input to the error system, which is the difference between the original input and the controller that we are designing for the first system. And then at the point, it's again a stabilization step. So again, from the literature, we know how to solve this problem, and we can find N2 that stabilize the aerodynamic by solving an LMI. So we can put everything together, and from data, from the X1 data, from the X2 data, and from the U1 data, we can solve the cascade stabilization problem. Now, one thing that I want to stress is the amount of samples that we need. And I want to stress the fact that by using this method, we save in number of samples. And the reason is that you see that to stabilize a system, you need these rank conditions over here. So you need that the rank of the state and U is full. You don't need that. As I said, you can relax this with an informative condition and so on. But if we look just at this rank condition, that's the amount of samples that you need, right? Now, that means that if we consider the interconnection of of the two systems, sigma 1 and sigma 2, as one system, then we know that the rank condition will be the sum of the size of the two states, so N1 plus N2, plus the number of inputs. So this is going to be the condition for the monolithic system obtained from the column of X1 and X2. Okay? If instead we use the cascade method, you see that the rank conditions are the rank conditions on the first system, which is N1 plus M1, the second system, N2 plus N1, and the third system, N2 plus M1. Now, in terms of amount of samples that we need to collect, the amount of samples is going to be at least this amount, or this amount, or this amount, because otherwise you cannot fulfill the rank condition. So this shows that if you use the forwarding method, the minimum amount of time is actually at least the maximum between these three numbers, which are in general less than this number here. Now, for two systems in cascade, this difference is little. For instance, if N1, N2, and M1 is all equal to N, then this is 3N, and this is 2N. So the saving is little. But as we can see later, actually, the saving in the cascade approach is, the amount of samples is constant. It's always going to be the maximum of all the rank conditions. So it does not depend on how many rank conditions you have. It depends only on the worst one. While in the monolithic case, the size of the system will sum, and so this will grow with the number of systems. And so the amount of data that you require in the monolithic case is much higher. Okay, so it's 45. Let me close this. So let me just comment briefly without going into the detail. We can look at the noisy version of this result of the cascade stabilization. We do the various procedures, and what we will end up with is that in the case of noise, so we have process noise, we have measurement noise, we don't have anymore the triangular structure that we had before, so we cannot stabilize anymore, but we can do a small gain argument. If the noise is not too big, we will have an input to state type of stability. So we will go close to zero, and we will be around zero, and a ball around zero, depending on the entity of the noise. So we can still do that. We can do the N cascade, so where we have many systems in cascade. And as I say, this will save on the number of samples that you need. And here there is a plot that shows this. So this is okay, this is essentially the formula that is here, but it's actually computed from measurements, so from actual experiments. So here sorry, so there is someone that was not muted. So
yeah, I think someone accidentally opened the mic. But,
yeah. So here, essentially, what we see is the following. We are making a simulation which we want to stabilize a cascade of 2 systems, then of 3 systems, or 4 systems, by up to 11 systems. The red line is the number of samples that we need using the approach that we propose, which is always constant, equal to the maximum size of these systems, which is, I think, 4 or 5, I don't remember, something like that, okay? While the black dots shows the number of samples required, otherwise it doesn't work. So the MATLAB doesn't give you the result. The number of samples for the monolithic approach. So instead of considering the cascade, you just consider a unique system. And what we see is that the minimum of samples increases with the number of systems in Cascade up to 5, and then it doesn't work anymore. And this doesn't work anymore because the LMI becomes bigger and bigger and bigger, and at a certain point the toolbox doesn't, I mean, it's a simple toolbox, doesn't solve the LMI anymore, okay? So the other advantage is not just in numbers of samples, but the fact that with our approach, you need to solve 11 small problems rather than one big problem, and this means that we can always solve it. And this can be seen also in the trajectories. So for instance, these are the trajectories of the last system in the Cascade of 5, so the last system for which the monolithic approach works, and you can see how worse the trajectories of the monolithic approach, so the black lines are. They are much more oscillatory because the optimization problem struggles to find a solution. So to conclude, you can then use this approach for solving problems like model reduction. I'm not going to explain this. And then also autoregulation, so tracking. And specifically, the autoregulation problem is solved by leveraging the cascade stabilization problem. So the autoregulation problem can be formulated as a cascade stabilization problem, and then we can solve that using those results and so on. So I don't want to go too much into the details. If you are interested, you can look at the paper. So the purpose here is to show you the idea. And then if you think that this is useful, you can look at the details in the paper. And so these are available on arXiv. Part 1 covers what I presented today, essentially. And part 2 presents the data-driven model reduction and the data-driven upregulation method. And with this, I conclude. Thank you very much for, I lost only 2 or 3 people, so that's good. Thank you very much for your attention. And if you have any questions, I'm happy to reply.
Thank you, Giordano, for the great talk. Any questions from the audience?
Oh.
Yes, Behrat, you can turn on the mic.
Yeah, hello, hi.
Hi.
First of all, I really wanted to thank you for your presentation. I really enjoyed listening to your presentation. And the only question that I wanted to ask is, like, in the fundamental lemma that you presented, you said, like, you need to have a rank condition on your data, right?
Yes.
So I just wanted to know if that rank condition is sufficient, or if it is satisfied, then we always know that matrix G exists. So it's essentially necessary and sufficient.
It is just sufficient. Okay, so this condition can be relaxed. Okay.
Mm-hmm.
So it's possible to show that there are cases in which you can solve the problem while this condition is not satisfied. Okay.
Mm-hmm.
That's called the informativity, essentially. The issue, and we could write it in that way. The issue is that it's not possible to verify it a priori, because one way of formulating that condition will be that theta C1 is in the image of x2 minus u2 minus, and this can be true even if x2 minus u2 minus is not full rank. But then there is no way of verifying this a priori, because you don't know what's theta and is. Okay, so that's why I prefer to write the rank condition, is because it's a condition that can be verified. Okay, but it can be relaxed. And if I can comment more. So as I said, there is a version of this result in which also sigma 1 is not available. And this will require its own rank condition. That rank condition cannot be relaxed. That rank condition is more sharp. Okay. Yeah.
Yeah, sure. So the only follow-up on that is, like, when this matrix is full row rank, it has right pseudo inverse, right? So a simple answer for matrix G is always to consider the right pseudo inverse of this matrix times to the left matrix in your equality. So as far as I can see, it seems like it always exists. So if this condition is satisfied.
Yeah, so if this condition is satisfied, you can use this identification to solve these problems. Okay, that's true. you can, but the point is that you can remove this condition. Okay, so this condition can be removed. I put it here just because it can be verified. From a computational point of view, I prefer it, but it's not needed. Okay, this condition is not needed. So this method works even when you cannot compute the pseudo inverse. And all the results that we provide are all without the pseudo inverse to exploit this possibility. That's one reason why we want to do that. The other reason is about the noise. So I didn't, I showed this very briefly about this bound, but this bound can be carried over in all the applications. So that means that we can find a bound on the final design controller, or for instance, a bound on the mismatch between the moments over here as a function of the initial error, which I think is not possible if you go through a system identification step first, and then you do the design.
Exactly. Yeah. Thank you very much. Thank you.
Thank you.
Do we have any other questions? If not, I have one about the sample size complexity that you mentioned, right, and the improvements that you get. Is it fair? So if I make a parallelism, is it fair to say that you kind of have you can think of this as a compositional approach, and in some way you replace a conjunction with a disjunction in terms of the sample size requirements, that you take the worst case sample requirements among the family of subsystems that you have, so the components that you put together, versus summing those up?
That's correct. Yes, it's a way of looking at this like this. Okay, and the reason that the saving comes from is the fact that the cascade has a structure. So if you think about, if you look at the monolithic approach and you look at data, you don't know that you have a block of zeros here, right? And so I think that's essentially why then there is this saving, and it comes exactly by that, is the fact that by doing a step at the time, you always keep the complexity at the worst complexity is the one of the worst step, rather than the sum of all of them.
Neither there exists necessarily a transformation so that you bring your original monolithic approach in a format that exhibits that structure.
So there was some problem with the audio, so I sampled some things. So you asked about a transformation, but a transformation between what?
I was wondering, can you hear me now or not?
I can hear you. Your your video doesn't work well, but I can hear you. Yeah. Yeah. No, I cannot hear you.
Yeah, your voice is interrupted on my end, but perhaps it's my problem. I don't know. I was wondering whether there exists a transformation in the original monolithic approach that could bring the metrics in that form, like you would do in Kalman decomposition-like transformation. Maybe it's not, right? It's a question due to ignorance. So
I didn't think about asking this question, so I'm not sure. I cannot give an answer, to be honest, whether there is a way of I need to think about also to formulate the question properly, exactly what is that we want to show. But it is not obvious to me anyway at the moment.
Okay.
Yeah.
Sounds good. Perhaps we can stop here. Giordano, many thanks once again for the excellent talk.
Thank you very much.
Introducing us to this topic. And thank you everyone for attending this webinar remotely.
Thank you. See you.
Thank you.
Bye-bye.
Thanks, everyone. Bye.
Bye. Thank you.